Welcome back to another journey through the quiet wonders of our world. Tonight we're going to explore volcanoes, those ancient mountains of fire that have shaped our planet since the very beginning, and continue to breathe and shift beneath our feet even now. If you enjoy these gentle explorations into science, consider subscribing to the channel so you can drift off to more curious discoveries in the nights to come. Now, let's begin. Before we talk about what volcanoes are, let's talk about what we call them. The word volcano comes from Vulcan, the Roman god of fire, who was believed to forge weapons beneath a volcanic island. The ancient Romans, watching smoke rise from Mount Etna in Sicily, imagined an entire workshop beneath the earth, a divine blacksmith hammering out thunderbolts and armor for the gods, the smoke rising from his forge, the rumble of the mountain, his hammer striking the anvil. It's a surprisingly poetic explanation for something so powerful, isn't it? They weren't entirely wrong, in a sense. Beneath volcanoes, there really is a forge of sorts, though what's being created isn't weapons, but new Earth itself. New rock, new land, new minerals cooling from liquid fire. The Romans couldn't have known about tectonic plates or magma chambers, but they understood something true. That volcanoes are places where the hidden becomes visible, where what dwells deep inside the earth occasionally rises to meet the sky. Even the name we use today carries that ancient sense of mystery and power, a reminder that humans have always tried to explain these mountains that breathe fire. There are approximately 1,500 potentially active volcanoes on Earth today. That might sound like a lot, and it is, but here's the gentle part. Only about 50 of them erupt in any given year. The rest spend their time in what we might call quiet slumber, breathing steam, occasionally rumbling, dreaming of fire but not yet ready to wake. Think of them as sleepers, some dozing lightly, others in deep hibernation that might last centuries or even millennia. A volcano can sit peacefully for so long that forests grow on its slopes, cities are built at its base, and people forget entirely that it's anything other than a mountain. Then one day, perhaps hundreds of years later, it remembers what it is. But most of the time, most volcanoes are patient. They wait, they rest. The earth is dotted with these sleeping giants, and the remarkable thing is how infrequently they actually stir. It's almost as if the planet has learned a kind of restraint, a rhythm where chaos is the exception rather than the rule. If you were to draw a line connecting most of Earth's active volcanoes, you'd trace out a shape, a horseshoe wrapped around the Pacific Ocean. This is called the Ring of Fire, and it contains about 75% of all the world's active volcanoes. It's not a coincidence, of course. This ring traces the edges of tectonic plates, those massive puzzle pieces of Earth's crust that are constantly, imperceptibly moving. Where these plates meet, where they grind against each other, or one slides beneath another, that's where volcanoes tend to appear. The Ring of Fire is really a ring of constant recycling, old oceanic crust diving down into the mantle, melting, and rising again as new volcanic rock. If you've ever wondered why the Pacific coastlines are so geologically dramatic, why Japan has so many earthquakes, why the Andes are still rising, why Indonesia is scattered with volcanic islands, this is why. The Pacific is surrounded by seams in the Earth's surface, and volcanoes are what grows along those seams. It's beautiful in a way, how geology creates patterns you can see from space. Scientists measure volcanic eruptions using something called the Volcanic Explosivity Index, or VEI for short. It ranges from 0 to 8, with 0 being a gentle, non-explosive eruption, and 8 being, well, something we've never witnessed in recorded history, though we know they've happened. The scale is logarithmic, which means each number represents eruptions 10 times more powerful than the one before. A VEI2 is 10 times bigger than a VEI1. A VEI3 is 10 times bigger than that. By the time you reach VEI8, you're talking about an eruption so massive it would eject more than 240 cubic miles of material and affect the entire planet's climate for years. The last one we know of was the Toba eruption about 74,000 years ago. Most eruptions we experience today are VEI 2 or 3, significant, yes, but not civilization-threatening. It's a reminder that even though volcanoes can be dangerous, truly catastrophic eruptions are mercifully rare. The Earth, for all its power, doesn't often unleash its full strength. In 1883, a volcano called Krakatoa erupted in Indonesia, and the sound it made was the loudest sound in recorded human history. People heard it 3,000 miles away. That's the distance from New York to Los Angeles. Or the pressure wave from the explosion circled the entire Earth 7 times, detectable on barometers around the globe. People 40 miles away had their eardrums ruptured by the sound alone. Try to imagine that for a moment. A sound so loud it travels across an entire ocean. A sound so powerful it physically injures people dozens of miles away. The eruption destroyed the island itself, leaving only fragments where a mountain once stood. The explosion was equivalent to 200 megatons of TNT, about 4 times more powerful than the largest nuclear weapon ever detonated. And yet, even after all that violence, the ocean eventually calmed. Fish returned. New volcanic islands began to form in the same spot. Nature, it seems, is both catastrophically destructive and quietly persistent in its renewal. When we picture lava, most of us imagine red or orange glowing flows, the colour of molten rock heated to extreme temperatures, and that's usually true. But not all lava glows red. Some volcanic flows glow blue, an electric, almost alien blue, and it's one of the most surreal sights in nature. This happens at places like Kawah Ijen volcano in Indonesia, where sulfuric gases emerge from cracks in the volcano and ignite when they contact the air. The flames themselves are blue, and when those flames heat sulfur deposits to their melting point, you get rivers of glowing blue liquid flowing down the mountainside in the darkness. It looks more like something from another planet than something from Earth. The miners who work there, collecting sulfur in the middle of the night, move through clouds of blue fire like figures in a dream. It's a reminder that even something as familiar as a volcano can surprise us, can show us colours and behaviours we didn't expect. The Earth still has secrets, even in phenomena we've studied for centuries. Not all volcanoes are explosive mountains. Some are gentle, built from thousands of quiet eruptions over millions of years, layer by layer, flow by flow. These are called shield volcanoes, and they're named for their shape. Broad and flat like a warrior's shield lying on the ground. The Hawaiian Islands are shield volcanoes built by lava that flowed like slow honey, spreading out in thin sheets rather than piling up in steep peaks. Mauna Loa, one of Hawaii's volcanoes, has been building itself for about 700,000 years. Each eruption adds a little more, raising the island a bit higher, extending the shoreline a bit further. There's something almost meditative about this kind of volcanism. No explosions, no dramatic pyroclastic clouds, just steady, patient construction. The lava emerges, flows, cools, and becomes land. Then it happens again and again. Over geologic time, this gentle persistence creates some of the most massive mountains on Earth. Measured from the seafloor, Mauna Loa is taller than Everest, but it built itself quietly, without fanfare, one layer at a time. In the year 79 AD, Mount Vesuvius erupted and buried the Roman city of Pompeii so quickly, so thoroughly, that it preserved an entire city like a time capsule. The pyroclastic surge, a fast-moving cloud of hot gas and volcanic matter, moved at about 180 miles per hour and reached temperatures high enough to kill instantly. The people of Pompeii were frozen in their final moments, their bodies later leaving cavities in the hardened ash that archaeologists filled with plaster to create casts. We can see a man shielding his face, a dog straining at its chain, families huddled together. It's deeply human and deeply sad. But it's also, in a strange way, a gift to history. Because Vesuvius buried Pompeii so completely and so quickly, the city wasn't looted or weathered away by centuries. Bread was preserved in ovens, graffiti remained on walls. We know what Romans ate, how they decorated their homes, what they wrote about politics and love. The same eruption that ended so many lives also preserved them in a way that lets us meet them, in a sense, almost 2,000 years later. Here's something that might seem contradictory at first. Volcanic soil is exceptionally fertile. The minerals that make volcanoes deadly, the elements released in eruptions, are the same ones that make the land around them bloom. This is why millions of people choose to live near active volcanoes despite the risk. The soil around Mount Vesuvius even now produces some of Italy's best tomatoes. The volcanic soils of Java support some of the densest agricultural populations on Earth. When lava weathers over time, it breaks down into soil rich in nutrients that plants desperately need: phosphorus, potassium, trace minerals. It's a kind of paradox. The same force that can destroy in an afternoon creates, over decades and centuries, conditions for extraordinary abundance. Perhaps that's why people return to volcanic slopes even after eruptions force them to flee. They know that eventually, after the ash settles and the rain comes, the land will be generous again. It's a trade-off people have been making for thousands of years. Here's a simple distinction that matters more than you might think. Magma becomes lava the moment it reaches Earth's surface. Before that moment, while it's still underground, it's called magma. After it emerges, it's lava. Same molten rock, just a different name depending on where it is. But that distinction marks something profound. The boundary between the hidden and the revealed, between potential and actual. Magma exists in chambers deep below us, sometimes for thousands of years, just waiting. We can't see it, can't touch it, can only infer its presence from earthquakes and ground deformation. Then one day it rises, breaks through, and becomes lava. Visible, undeniable, flowing down the mountain for everyone to see. In a sense, every volcanic eruption is a moment when the Earth reveals a secret it's been keeping, when the inner world becomes outer. The name changes because the context changes, because once molten rock meets air and light, it becomes part of our world in a way it wasn't before. The temperature of lava can reach around 2,200 degrees Fahrenheit. That's about 1,200 degrees Celsius if you prefer. To put that in perspective, it's hot enough to melt most rocks, hot enough to vaporize water instantly, hot enough to ignite trees before it even touches them, and yet it's still cooler than the surface of the sun. There's something almost gentle about how lava moves, despite its impossible heat. It flows like slow honey, oozing down slopes, curling around obstacles, sometimes moving so slowly you could walk alongside it, though you wouldn't want to, given the radiant heat. This contradiction between appearance and reality is part of what makes lava so mesmerizing to watch. From a safe distance, it almost looks peaceful, the way it glows and flows, the way it seems to move with intention, finding paths downhill like water. But get too close and you'd feel the heat pulsing against your skin, a reminder that what looks serene is actually one of the most destructive forces in nature. Maybe that's why people are drawn to watch lava flows despite the danger. There's something hypnotic about seeing such power move so slowly, so deliberately. Iceland sits atop the mid-Atlantic ridge, which is the place where two of Earth's tectonic plates, the North American and the Eurasian, are slowly pulling apart. This means Iceland is literally being torn in two, though so slowly you'd never notice in a human lifetime. The island grows wider by about an inch each year, pulled in opposite directions by the movement of continents. You can actually visit places in Iceland where you can stand with one foot on the North American plate and one on the Eurasian plate, straddling the gap between them. This rifting is also why Iceland is so volcanically active. As the plates separate, they create space for magma to rise from the mantle below. The island is, in a very real sense, being constantly rebuilt from the inside out. Old Iceland on the coasts, New Iceland forming along the central rift. In millions of years, Iceland might be two separate islands, drifting further apart. But for now it holds together. A land defined by the tension between forces trying to pull it apart and the volcanic activity that keeps filling in the gaps. If you want to find the largest volcano in our solar system, you'd need to leave Earth entirely and travel to Mars. There, rising from the Tharsis Plateau, stands Olympus Mons, a shield volcano so massive it makes anything on Earth look modest by comparison. It stands about 3 times taller than Mount Everest, rising roughly 16 miles above the surrounding plains. But what's even more impressive is its width. The base of Olympus Mons is approximately the size of Arizona. If you stood at its center, you wouldn't be able to see the edges. They'd be beyond the horizon, and if you stood at its base looking up, you wouldn't see the summit. It would be too far away, curved beyond the horizon in the other direction. The peak rises so high that it breaks through much of Mars's thin atmosphere. Standing on top, you'd essentially be in space. What created such a massive volcano? Mars lacks plate tectonics, so volcanic hotspots don't move. On Earth, as plates shift, hotspots create chains of volcanoes, like the Hawaiian Islands. On Mars, the hotspot just kept feeding the same volcano for millions of years, building it higher and wider until it became this incomprehensible mountain. It's been dormant for millions of years now, a monument to forces that once shaped a world but have since gone quiet. Some volcanic eruptions are so powerful that they blast material into the stratosphere, the layer of atmosphere where weather doesn't happen, where the air is thin and still. And when volcanic debris reaches those heights, it can stay suspended for years, circling the globe, affecting climate across the entire planet. The 1815 eruption of Mount Tambora in Indonesia was one of these. It ejected so much material that the following year, 1816, became known as the year without a summer. Snow fell in New England in June. Crops failed across Europe. Temperatures dropped worldwide. People who lived through it had no idea why the seasons had gone wrong. They didn't have the scientific framework to connect a distant volcanic eruption to failing harvests halfway around the world. But the connection was real. The sulfur dioxide released by the eruption formed tiny droplets in the stratosphere that reflected sunlight back into space, cooling the Earth below. It's a sobering reminder of how interconnected our planet systems are. Yeah, how an event on a remote Indonesian island can change the weather in Switzerland, can cause famines in China, can alter the course of history in ways the people experiencing it might not understand. During volcanic eruptions, something extraordinary sometimes happens in the ash clouds. Lightning. Not the lightning we're used to from thunderstorms, but volcanic lightning, created when ash particles collide with each other during an eruption, generating static electricity. These electrical storms are sometimes called dirty thunderstorms, and they're among the most spectacular light shows in nature. Imagine towering columns of ash rising miles into the sky, and within them brilliant bolts of lightning arcing between particles, illuminating the cloud from within like a living thing. The lightning is often reddish or orange because of the glow from the hot ash, creating colours you'd never see in a normal thunderstorm. Scientists are still studying exactly how volcanic lightning forms. The mechanisms aren't entirely understood yet, but we know it happens when particles of different sizes collide at different speeds, stripping electrons from each other until the electrical potential difference becomes so great that it discharges in brilliant arcs. It's one of those phenomena that seems almost too dramatic to be real, like something from mythology, and yet it happens every so often when conditions are right. Kilauea, on the big island of Hawaii, holds an unusual record. It has been erupting almost continuously since 1983. That's more than 4 decades of eruption, though not in the explosive, catastrophic sense. Kilauea's eruptions are relatively gentle, producing lava flows that move slowly enough that people can evacuate, though not always fast enough to save their homes. In all that time, this ongoing eruption has added more than 500 acres of new land to the island, lava flowing into the ocean, cooling and becoming solid ground where there was once only water. You can watch this process happen. Stand on the coast and you'll see rivers of molten rock pouring into the sea, creating clouds of steam, hissing and boiling, and when the steam clears, there's new land that wasn't there before. It's creation in the most literal sense, the planet making more of itself right before your eyes. The people of Hawaii have learned to live with Kilauea's constant activity, to respect it, even to find a kind of peace with it. The volcano is part of the landscape, part of the culture, part of the rhythm of life on the island. It's not a disaster. It's just what the mountain does. We tend to think of volcanoes as terrestrial features, mountains on land, but the truth is that submarine volcanoes, the ones hidden beneath the ocean, outnumber land volcanoes by an estimated 10 to 1. Most of Earth's volcanic activity happens underwater, in places we've barely explored. The mid-ocean ridges, those underwater mountain ranges where tectonic plates pull apart, form a continuous volcanic system about 40,000 miles long, longer than any mountain range on land. These ridges circle the planet like the seams on a baseball, and along those seams, new oceanic crust is constantly being formed from erupting lava. We know more about the surface of Mars than we do about these underwater volcanic systems. They're hard to study, deep, dark, under immense pressure, but they're fundamental to how our planet works. Every bit of oceanic crust on Earth came from underwater volcanic eruptions at mid-ocean ridges. The ocean floor is constantly being made and remade, a process that happens mostly in silence and darkness, witnessed by no one. It's humbling in a way to realize that the majority of our planet's volcanic activity happens in a realm we can barely access. Pumice is a curious rock, the only rock that floats. It forms when lava that's full of gas bubbles cools so quickly that the bubbles get trapped inside, creating a rock that's mostly empty space, so light and porous that it sits on the surface of water rather than sinking. After large volcanic eruptions, particularly ones near the ocean, vast rafts of pumice can drift across entire ocean basins, sometimes for years. These floating rocks become accidental ferries for marine life. Barnacles attach to them. Algae colonize them. Small creatures hitch a ride. By the time the pumice finally becomes waterlogged enough to sink, it may have travelled thousands of miles, depositing its passengers in new habitats where they might never have reached otherwise. It's an unexpected form of dispersal, a way that volcanic eruptions contribute to the spread of life rather than just its destruction. There's something poetic about it. Rocks lighter than water, carrying life across oceans, the same eruption that devastated one place inadvertently seeding life in another. Nature rarely does just one thing at a time. Then the viscosity of lava, basically how thick and sticky it is, determines almost everything about how a volcano erupts. Think of it like the difference between water and honey. Thin, runny lava, low in silica, flows easily and creates gentle, effusive eruptions like those in Hawaii. You get lava fountains, flowing rivers of molten rock, but not massive explosions. Thick, viscous lava, high in silica, is different. It doesn't flow easily. Gases get trapped inside it, building pressure, until eventually the pressure becomes too great and the whole thing explodes violently. This is what happened at Mount St. Helens in 1980. The lava was so viscous that gases couldn't escape, and the entire north side of the mountain blew apart in a catastrophic eruption. It's the same substance, molten rock, but the chemistry determines whether you get a slow, predictable flow or a sudden devastating explosion. Volcanologists can sometimes predict how a volcano will behave just by analysing the composition of early erupted material. High silica content. Everyone needs to evacuate because an explosion is likely. Low silica. There's more time, more room for monitoring and decision-making. The difference matters enormously. Volcanic gases are a complex mixture. Water vapour makes up the majority, but there's also carbon dioxide, sulfur dioxide, hydrogen, sulfide, and trace amounts of other compounds. Some of these gases are toxic. Some create acid rain. Some contribute to the greenhouse effect. But here's something surprising. Volcanic gases sometimes contain microscopic particles of gold. When magma rises from deep in the earth, it can carry dissolved metals, including gold, and as the gases escape at the surface, some of that gold gets deposited or released into the atmosphere as tiny particles. Over Earth's long history, volcanoes have likely deposited thousands of tons of microscopic gold into the air, onto the land, into the oceans. Most of it is in such small concentrations that it's impossible to extract economically, but it's there nonetheless. A dusting of precious metal scattered across the world by fire mountains. It's a reminder that volcanoes aren't just destroying and creating rock. They're bringing up materials from deep inside the earth that would otherwise remain forever hidden, redistributing the planet's treasury bit by bit. The largest volcanic eruption in recorded human history was Mount Tambora in 1815, which we mentioned briefly before. But let's sit with the scale of it for a moment. Yeah, this eruption ejected approximately 36 cubic miles of material into the atmosphere. To help visualize that, and these numbers are so large they're hard to grasp, that's enough volcanic debris to bury the entire island of Manhattan under a layer 30 miles deep. The mountain itself lost about 4,000 feet of elevation, its peak simply gone, replaced by a massive crater. The immediate blast killed tens of thousands of people. The global climate effect killed far more through famine and disease over the following years. And yet, if you visit Tambora today, you'd find a mountain that looks peaceful, covered in vegetation, with a beautiful crater lake at its summit. Nature has softened the evidence of catastrophe. The forests have returned. Life continues. It's almost impossible to stand there and imagine the violence that occurred, the scale of destruction. But that's often true of volcanic landscapes. They heal, they green over, they invite life back. The mountain remembers perhaps in the layers of rock that geologists can read like a history book, but the surface forgives and forgets. Volcanoes can create their own weather systems, which sounds almost impossible until you think about what they're doing, injecting enormous amounts of heat and moisture into the atmosphere all at once. During eruptions, the rising column of hot ash and gas can generate localized rain, lightning, and even tornadoes. These aren't weather patterns that exist anywhere else on Earth. They're unique to the violence of eruption. The heat creates powerful updrafts, moisture condenses, storm systems form around the eruption column itself. Then sometimes it rains mud, a combination of volcanic ash and water that falls like thick, gritty precipitation. These volcanic weather systems can persist for hours or even days during major eruptions, creating a chaotic atmospheric environment directly above the mountain. It's weather without the usual rules, driven by forces more powerful than typical meteorological patterns. And then, when the eruption ends, these weather systems simply dissipate, as if they were never there. The sky's clear. Normal weather patterns reassert themselves. But during the eruption, the volcano is essentially its own climate zone, a pocket of atmosphere behaving according to different physics. When we look at the Hawaiian Islands, we see tropical peaks rising from the ocean. But what we're actually seeing is just the tip of something much larger. The Hawaiian Islands are the peaks of massive shield volcanoes that rise from the ocean floor, and when you measure them from their true base on the seafloor rather than from sea level, they're taller than Mount Everest. Mauna Kea, measured from its underwater base to its summit, rises about 33,500 feet, more than 4,000 feet taller than Everest. Of course, most of that height is hidden beneath the Pacific Ocean, invisible to us. But it's there. The Hawaiian Islands are among the tallest mountains on Earth. We just don't usually think of them that way because we measure mountains from sea level, not from their geological base. It changes your perspective, doesn't it? These islands that seem modest compared to the Himalayas are actually towering volcanic edifices. They are built up from the deepest parts of the ocean floor through millions of years of eruptions. The ocean hides their true scale. Stand on a Hawaiian beach and you're at the top of a mountain that stretches down into darkness, down to where the pressure would crush you, down to where the volcano first began building itself thousands of millennia ago. Fact 24. Despite its name, volcanic ash isn't actually ash in the way we usually think of it, the soft powdery residue left after burning wood. Volcanic ash is made of tiny fragments of pulverized rock and volcanic glass, created when magma shatters explosively during eruptions. Each particle has sharp, jagged edges, which is why volcanic ash is so much more dangerous than it might seem. It can abrade and damage jet engines, which is why aircraft avoid volcanic ash clouds at all costs. When inhaled, it can irritate and damage lung tissue because those microscopic shards of glass and rock create tiny cuts in the respiratory system. It's heavy when it accumulates. Roofs can collapse under the weight of thick ash deposits. It doesn't dissolve in water. Instead, it turns into a kind of cement-like slurry that clogs drainage systems and makes roads impassable. And yet, over time, this same ash weathers into fertile soil. The sharp edges wear down. The minerals become available to plants. What was dangerous becomes nourishing. But in the immediate aftermath of an eruption, volcanic ash is one of the most challenging hazards to deal with. Not dramatic like lava flows, but insidious, getting into everything, causing problems for months or even years after the eruption ends. The Greek island of Santorini, with its whitewashed buildings clinging to cliffs overlooking a blue caldera, is one of the Mediterranean's most beautiful destinations. But that caldera, the water-filled depression at the centre of the island group, is actually the collapsed heart of a massive volcano that erupted around 1600 BC. The eruption was so powerful it destroyed the centre of the island, leaving only the rim that we see today. Some scholars believe this eruption may have inspired the legend of Atlantis, Plato's story of an advanced civilization that disappeared in a single day and night. The timing is right. The location is right. An island civilization in the Mediterranean, destroyed by a natural catastrophe. The Minoan civilization on Crete nearby was severely affected by the eruption, possibly contributing to its decline. We'll never know for certain if this is the source of the Atlantis legend, but there's something compelling about the idea that one of Western civilization's most enduring myths might have originated from a real volcanic catastrophe. Either way, Santorini today is peaceful, beautiful, and popular with tourists who might not realize they're swimming in the flooded crater of one of the ancient world's most destructive volcanoes. Lava tubes are natural tunnels that form in a peculiar way. When lava flows down a slope, the surface that's exposed to air cools and hardens first, forming a crust. But underneath that hardened roof, the lava is still molten and continues flowing downhill, like water through a pipe. Eventually the eruption ends, the lava drains away, and what you're left with is an empty tunnel. A lava tube. Yet some of these tubes are enormous. In Hawaii there are lava tubes large enough to drive a bus through, extending for miles underground in complete darkness. They're remarkably stable structures. Their hardened lava forms a strong arch that can last for thousands of years. People have explored lava tubes, walked through them with flashlights, marvelled at their smooth walls and the evidence of where lava once flowed along the ceiling. In some places, lava tubes have collapsed, creating skylights where sunlight streams down into the tunnel. Plants grow in these openings, creating little gardens in the middle of the dark tube. There's something almost cathedral-like about being inside a large lava tube. The arched ceiling, the sense of vast underground space, the silence. They're monuments to vanished rivers of fire. Beneath Yellowstone National Park lies one of Earth's supervolcanoes, a volcanic system so large that the caldera at the surface is measured in dozens of miles rather than hundreds of feet. The magma chamber beneath Yellowstone is enormous, roughly 55 miles long and 20 miles wide, though it's not a single hollow chamber, but rather a complex zone of partially molten rock extending deep into the earth. This system has erupted 3 times in the past 2.1 million years, 640,000 years ago, 1.3 million years ago, and 2.1 million years ago. Each eruption was massive enough to reshape the landscape of North America, covering vast areas in volcanic ash. The most recent eruption created the Yellowstone caldera that exists today. Though you'd never know it's a caldera just by looking, it's so large that it wasn't even recognized until aerial photography and geological surveys revealed its circular structure. Should it erupt again at that scale, it would be catastrophic for the continent. But here's the important part. There's no indication that such an eruption is imminent. Yellowstone is monitored constantly, and while the ground does rise and fall as magma shifts below, the system appears stable for now. Supervolcanoes operate on geological timescales, and hundreds of thousands of years might pass before the next major eruption. When massive volcanic eruptions inject huge amounts of sulfur dioxide into the stratosphere, they can trigger what are called volcanic winters, periods of significant global cooling that can last for years. The sulfur dioxide combines with water vapor to form tiny droplets of sulfuric acid that hang suspended in the stratosphere, forming a reflective haze that bounces sunlight back into space before it can warm the Earth's surface. The result is a drop in global temperatures, sometimes by several degrees. Crops fail, growing seasons shorten, ecosystems struggle, and then, gradually the aerosols fall out of the atmosphere, the haze clears, and temperatures return to normal. But during those years of cooling, the effects can be devastating for human societies dependent on agriculture. The eruption of Mount Pinatubo in 1991 cooled the Earth by about 0.5 degrees Celsius for 2 years. It doesn't sound like much, but 0.5 degree globally is enormous, enough to affect weather patterns worldwide, to change rainfall distributions, was to impact harvests. Ironically, some scientists have suggested that volcanic aerosols might offer a model for geoengineering to combat global warming, deliberately injecting particles into the stratosphere to reflect sunlight. But it's a controversial idea because volcanic winters, even temporary ones, cause their own kinds of suffering. Here's something that seems almost magical. Some volcanoes emit diamond particles. Not large diamonds, mind you. These are microscopic crystals, formed when carbon-rich magma rises very rapidly from deep in the mantle, where pressures are immense. At those depths, carbon can crystallize into diamond form, and if the magma rises fast enough, those tiny diamonds survive the journey to the surface rather than converting back into graphite. They're scattered in volcanic rocks, invisible to the naked eye. But there nonetheless. It's a reminder of the tremendous pressures and temperatures that exist beneath us. The diamonds we mine from kimberlite pipes, those vertical columns of volcanic rock, got there the same way, brought up from the mantle by ancient volcanic eruptions. Every diamond ever found came from deep inside the earth and was carried upward by volcanic forces. We tend to think of diamonds as precious and rare, but in geological terms they're just another form of carbon that occasionally makes its way to the surface when conditions are right. The volcano doesn't care about their value. It's just bringing up whatever was down there, gems and minerals mixed indiscriminately with common rock. In East Africa, something remarkable is happening in slow motion. A new ocean is being born. The Great Rift Valley is a place where the African continent is literally tearing itself apart, pulled by tectonic forces that are slowly ripping the continent into separate pieces. Volcanic activity is a key part of this process. As the land stretches and thins, magma rises from below, creating volcanoes all along the rift. Eventually, in a few million years, the rift will open wide enough that seawater will flood in, and East Africa will become a separate island, drifting away from the main continent like Madagascar did tens of millions of years ago. We're witnessing the earlier stages of this process right now. The rift is widening by a few millimeters each year, imperceptible in human terms, but geologically it's happening quickly. The volcanic activity in the region is part of this breaking apart. The Earth's way of filling in the gaps as the crust stretches. It's a reminder that the map of the world is not permanent, that continents are always moving, always changing shape, and that volcanic activity is often the mechanism by which these grand tectonic dramas unfold. In Hawaiian, there are two words for lava that describe not its temperature or composition, but its texture and behaviour. Pahoho, pronounced pahoihoi, is smooth and ropey, flowing in billowy, undulating patterns that look almost organic, like frozen waves or coiled rope. Ah, pronounced ah, is rough, chunky, and jagged. The kind of lava that would shred your shoes if you tried to walk across it, with sharp clinkers and broken fragments piled chaotically. Here's the interesting part. The same lava flow can transform from Pahoho to Ea as it travels downslope. When the lava first emerges, it's often hot enough and gas-rich enough to flow smoothly as Pahoho. But as it cools and loses gas, it becomes more viscous, and the smooth flow breaks apart into rough Aa. It's like watching lava change its personality mid-journey, going from fluid and graceful to fractured and aggressive. The Hawaiians who named these lava types lived with volcanoes intimately, watching eruptions regularly, walking across fresh lava fields, and they needed precise language to describe what they saw. Pahoho you might be able to cross carefully, Ea you avoid entirely. The words carry practical wisdom encoded in their sounds. Even saying A sounds sharp and broken, doesn't it? Language shaped by living on the slopes of active volcanoes. At the bottom of the world in Antarctica, there's a volcano that erupts in one of the coldest, driest, most inhospitable places on Earth. Mount Erebus sits on Ross Island, surrounded by ice, and it's the southernmost active volcano on the planet. What makes it even more remarkable is that Erebus contains a permanent lava lake, one of only a few in the world, where molten rock sits exposed at the surface year-round, glowing red against the Antarctic cold. The contrast is surreal. Temperatures outside can drop to minus 40 degrees or colder, while just a few hundred feet away, lava churns at 1,700 degrees Fahrenheit. Steam and volcanic gases rise continuously from the crater, creating ice towers called fumarole spires, where the hot gases freeze as they meet the Antarctic air. These ice formations can grow to enormous sizes, some reaching heights of 60 feet, sculpted by wind and volcanic breath into bizarre hollow chimneys. Scientists study Erebus because it's so unusual, and because its persistent lava lake gives them a window into ongoing volcanic processes that are usually hidden inside vents. But there's also something almost philosophical about it, this meeting of absolute opposites, fire and ice coexisting in the same place, neither one winning, both just being what they are. Every breath you take contains molecules that once escaped from volcanic vents billions of years ago. Volcanoes played a crucial role in creating Earth's atmosphere and oceans through a process called outgassing. In the planet's early history, volcanic eruptions released enormous amounts of water vapor, carbon dioxide, nitrogen, and other gases that had been trapped in the rocks of the young Earth. Over time, this water vapor condensed and fell as rain, probably thousands of years of continuous rain filling the ocean basins. The gases formed the early atmosphere. Without volcanic outgassing, Earth would have remained a dry, airless rock. Instead, volcanoes gave us the sky and the sea. It's humbling to think about. The water you drink, the air you breathe, they're gifts from ancient volcanic activity, from a time when the whole planet was more volcanically active than it is now. Even today, volcanoes continue to add small amounts of water and gases to the atmosphere, maintaining this exchange between Earth's interior and its surface. We often think of volcanoes as purely destructive, but in the deepest sense, they're creative forces. They helped make our world habitable, gave us the conditions necessary for life to begin. If you've ever seen photographs of Hawaii's green sand beaches, you might have wondered how sand becomes green. The answer lies in a mineral called olivine, a semi-precious stone that forms deep in Earth's mantle and is common in certain volcanic rocks. When olivine-rich lava erupts and eventually weathers and breaks down, the olivine crystals are released. They're heavier than most other sand particles, so while lighter materials get carried away by waves and currents, the olivine accumulates, creating beaches with a distinctive olive-green colour. Walking on these beaches means you're walking on crystals that form dozens of miles below the surface, in the hot, high-pressure environment of the mantle, brought up by volcanic activity and then liberated by the patient work of waves and weather. It's strange to think about, isn't it? So these tiny green grains under your feet came from a place no human could ever visit, from depths where the rock is partially molten and the pressure would instantly crush anything from the surface. But volcanic eruptions bring samples up, and time breaks them into sand, and eventually they wash up on a beach where someone might notice how the sunlight makes them sparkle, not knowing they're looking at fragments of Earth's hidden interior. During Hawaiian eruptions, when droplets of lava are thrown into the air and stretched by the wind, they sometimes form thin strands of volcanic glass called Pele's hair, named after Pele, the Hawaiian goddess of volcanoes. These strands are remarkably delicate, golden brown or sometimes almost transparent, and they can be stretched to incredible thinness, finer than human hair. When strong winds blow during an eruption, Pele's hair can drift for miles, accumulating in sheltered spots where it looks like golden fiberglass insulation. It's fragile. Touch it and it breaks. But while it lasts, it's beautiful in a strange, unearthly way. Sometimes there are also Pele's tears, small, solidified droplets of lava that form at the same time, the blobs of molten rock that were stretched into hair, but also dropped bits that cooled into teardrop shapes. Together, the tears and hair create this surreal landscape around Hawaiian vents, golden strands scattered across black lava rock. The Hawaiians saw these formations and interpreted them as signs of the goddess, her hair, her tears, and it's easy to understand why. They don't look like ordinary volcanic products. They look like something left behind by a presence, traces of something that passed through and touched the landscape in a moment of creation or sorrow. The volcanic hotspot that created the Hawaiian Islands and continues to feed Kilauea's eruptions today is thought to be fed by a deep mantle plume, a column of unusually hot rock rising from far below the tectonic plates. These plumes may originate nearly 2,000 miles beneath the surface, perhaps from near the boundary between Earth's mantle and its liquid iron core. That's almost halfway to the center of the planet. The rock in these plumes is hotter than the surrounding mantle, so it's less dense, and it rises like a blob of wax in a lava lamp, slowly ascending through the mantle over millions of years until it finally reaches the base of the crust. There it melts through, creating volcanoes at the surface. But here's the interesting part. The hotspot stays relatively fixed while tectonic plates move over it. So as the Pacific plate drifts northwest, it carries old Hawaiian volcanoes away from the hotspot, where they become extinct, while new volcanoes form over the hotspot to replace them. This is why the Hawaiian Islands form a chain, with the oldest islands in the northwest and the youngest, the Big Island with its active volcanoes in the southeast. Eventually the Big Island will drift away too, and a new island, already forming underwater as a seamount called Loihi, will take its place. The cycle continues, driven by forces so deep we can only study them indirectly. In Iceland, there's a town called Grindavik that sits directly above an active volcanic system, a place where eruptions can happen with relatively little warning, where the ground can crack open and lava can emerge almost anywhere. And yet, people continue to live there. They've evacuated multiple times in recent years when volcanic activity increased, only to return when things calm down. Why do they stay? For many, it's a combination of factors. The geothermal energy that heats their homes cheaply and sustainably, the fertile volcanic soil, the fishing industry supported by the nearby ocean, and perhaps most importantly, a sense of place, of belonging to a landscape despite its dangers. There's something deeply human about this choice to live with risk when the place feels like home. It's easy to say from the outside that people should just move, should relocate somewhere safer. But home isn't always a rational decision. The people of Grindavik, like millions of others who live near active volcanoes around the world, have made a calculation, conscious or not, that the benefits outweigh the risks, that the richness of life in a volcanic landscape is worth the occasional need to flee, to rebuild, to start again. It's a trade-off humans have been making for thousands of years. Obsidian is volcanic glass, formed when lava cools so rapidly that the atoms don't have time to arrange themselves into orderly crystal structures. Instead, they freeze in place randomly, creating glass rather than crystalline rock. The result is a material that's incredibly sharp when broken, sharper than surgical steel in fact. Ancient cultures discovered this and treasured obsidian for making cutting tools, arrowheads, and blades. Some cultures used polished obsidian as mirrors, dark and reflective, we sometimes attributed with mystical properties. There's archaeological evidence of obsidian being traded over vast distances in the ancient world. Obsidian from volcanic sources in Anatolia has been found in Mesopotamia, hundreds of miles away, indicating how valued it was. What's remarkable is that we can trace obsidian artifacts back to their source volcanoes by analysing their chemical composition. Each volcanic source has a unique signature, which tells us about ancient trade routes and cultural connections. Today, some surgeons use obsidian scalpels for certain delicate procedures because the edge is finer and sharper than metal blades. So this volcanic glass that forms in moments of rapid cooling has been useful to humans for tens of thousands of years. From prehistoric toolmaking to modern surgery, they're the same material serving the same purpose, to cut cleanly and precisely. Mount Fuji, Japan's most iconic mountain, last erupted in 1707, more than 300 years ago. That eruption, called the Hoei eruption, deposited ash on Edo, now Tokyo, about 60 miles away, and caused significant damage. Since then, Fuji has been quiet, and yet it's still classified as active, still monitored continuously, because from a geological perspective, 300 years is not a long silence. Fuji could erupt again tomorrow, or it might sleep for another 1,000 years. We don't know. What's interesting is how this uncertainty exists alongside Fuji's enormous cultural significance to Japan. The mountain is sacred in Shinto belief, painted countless times by artists like Hokusai, climbed by hundreds of thousands of pilgrims and tourists each year. However, there's almost a sense of patience around Fuji, as if the mountain's silence is a kind of restraint rather than true dormancy. The Japanese people live with this duality. Fuji as a symbol of natural beauty and spiritual importance, and Fuji as a potentially active volcano that could, without much warning, remind everyone of what it really is. That these two understandings coexist is part of what makes the relationship between Japan and its most famous mountain so complex and fascinating. Deep beneath active volcanoes, magma doesn't move in silence. As it rises through cracks in the rock, as it fills and drains chambers, it creates vibrations, continuous rhythmic trembling called volcanic tremor. It's different from earthquakes, which are sharp jolts. Volcanic tremor is more like a sustained hum, a vibration that can last for hours or days, and seismometers detect it easily, and to volcanologists it's one of the most important warning signs that magma is on the move. In a way, volcanic tremor is like the mountain's heartbeat, a rhythm that tells you something alive, in a geological sense, is happening underground. Sometimes you can feel it if you're close enough, a subtle vibration in the ground beneath your feet, a reminder that the earth is not as solid and stable as it appears. For people who live near active volcanoes, this tremor is familiar, a background sensation during active periods. It's usually not dangerous by itself, but it's a signal. Listen. The magma is rising. Things are changing, stay alert. The mountain is breathing, shifting, preparing for something. Maybe a small eruption, maybe nothing, but the tremor tells you the volcano is awake and thinking about it. In 1991, Mount Pinatubo in the Philippines erupted in what would become the second largest volcanic eruption of the 20th century. The eruption was enormous, ejecting billions of tons of material into the atmosphere, including massive amounts of sulfur dioxide that formed aerosols in the stratosphere. These aerosols created a thin haze that encircled the entire planet, reflecting sunlight back into space and cooling the Earth's surface by about 0.5 degrees Celsius for the next 2 years. That might not sound like much, 0.5 degree, but on a global scale it's significant. Weather patterns shifted, growing seasons changed. Scientists were able to measure the cooling effect precisely, and it provided a real-world demonstration of how volcanic eruptions can temporarily counteract global warming, at least in terms of temperature. Of course, the cooling came with costs, disrupted agriculture, altered rainfall patterns, and all the immediate destruction from the eruption itself. But it gave climate scientists valuable data about how aerosols in the stratosphere affect planetary temperature, information that's now part of discussions about potential geoengineering solutions to climate change. Mount Pinatubo's eruption was a natural experiment on a planetary scale, and we learned from it, even as thousands of people lost their homes and had to rebuild their lives in the aftermath. In the boiling hot springs around volcanic vents, in water that would cook you in seconds, there are bacteria thriving. Not just surviving, but flourishing at temperatures exceeding 200 degrees Fahrenheit, in conditions that would denature the proteins of almost any other form of life. Yet these extremophils, as they're called, have fundamentally rewritten our understanding of what life requires. Before we discovered them, we thought life needed relatively narrow conditions: moderate temperatures, liquid water, certain chemical ranges. But these bacteria live in near-boiling acidic water, in environments that seem more like industrial waste than habitats for living things. Some of them don't even use oxygen. They metabolize sulfur or other chemicals. The discovery of extremophiles in volcanic environments has profound implications for astrobiology, the study of potential life elsewhere in the universe. If life can thrive in the harsh conditions around volcanic vents on Earth, then perhaps it could exist in the sulfuric clouds of Venus, or in the subsurface oceans of Europa, or around hydrothermal vents on distant moons. Volcanic environments, which we once thought of as inherently hostile to life, turned out to be home to some of the most resilient organisms on the planet, organisms that have expanded our sense of what's possible. Volcanic islands can rise from the ocean floor with remarkable speed. In 1963, off the southern coast of Iceland, fishermen noticed something strange. The ocean was roiling and steaming. Within days, a new island had emerged, built by an underwater volcanic eruption that brought rock and ash above sea level. They named it Surtsey, after Surtur, a fire giant from Norse mythology. Over the following years, the island grew through continued eruptions, eventually stabilizing at about half a square mile in size. What made Surtsey scientifically valuable was its pristine nature, a brand new landmass with no life on it, no soil, nothing but bare volcanic rock. Scientists immediately recognized it as an unprecedented opportunity to study how life colonizes new land, so they restricted access and began documenting every plant seed that arrived, every bird that nested, every insect that established itself. Over the decades, they've watched as Surtsey transformed from barren rock to an island with vegetation, nesting seabirds, and even a developing ecosystem. It's a time-lapse of ecological succession, showing us how life finds its way to even the most desolate places, how given time, the volcanic rock becomes soil, the soil becomes home. Near volcanic hot springs and hydrothermal areas, you sometimes find a mineral called cinnabar, a striking, vivid red compound that's the primary ore of mercury. Ancient cultures prized cinnabar for its colour, grinding it into pigment for paint and cosmetics. The Romans used it lavishly. Chinese emperors desired it. Artists throughout history used it to create brilliant reds in their work. What they didn't fully understand was that cinnabar contains mercury, a toxic heavy metal that accumulates in the body and causes neurological damage. Miners who extracted cinnabar often suffered from mercury poisoning. People who used cosmetics containing cinnabar sometimes experienced tremors, mood changes, cognitive decline. The beautiful red pigment was slowly poisoning them. Mercury has this strange property. It's liquid at room temperature, and it vaporizes slowly, so you can be exposed just by being near it. The connection between cinnabar, volcanoes, and mercury is ancient. Volcanic systems bring mercury up from deep in the earth, where it concentrates around hot springs and fumaroles. Even today, volcanic regions can have elevated mercury levels in soil and water. It's a reminder that not everything volcanoes bring to the surface is beneficial, that the same geological processes that enrich soil with nutrients can also concentrate toxic elements. Volcanoes release about 200 million tons of carbon dioxide into the atmosphere every year through eruptions and passive degassing. That sounds like an enormous amount, and in absolute terms, it is. But here's the perspective that matters. human activities, primarily burning fossil fuels, release about 100 times more CO2 annually than all of Earth's volcanoes combined. So while volcanic CO2 has been part of Earth's natural carbon cycle for billions of years, contributing to the greenhouse effect that keeps the planet warm enough for liquid water, it's dwarfed by anthropogenic emissions. Still, volcanic carbon is important to understand because it's been cycling through Earth's systems since the beginning. Volcanoes release CO2, which is absorbed by weathering rocks and by the ocean, which eventually gets locked into sediments, which gets subducted back into the mantle, which eventually release it again through volcanoes. It's a cycle that operates over millions of years, maintaining a rough balance. Human emissions are different. We're releasing carbon that was locked away in underground deposits for hundreds of millions of years, dumping it into the atmosphere faster than natural systems can absorb it. So volcanic carbon is part of the planet's breathing, while human carbon is something else, something new in Earth's long history. In western India, there's a region called the Deccan Traps, a massive plateau built from layer upon layer of ancient lava flows, covering an area larger than France. These aren't the remains of a single eruption, but rather one of the largest volcanic events in Earth's history. A series of eruptions that lasted for perhaps 1 million years, around 66 million years ago. At their peak, these eruptions may have released enormous amounts of lava and volcanic gases, potentially affecting global climate severely. The timing is significant. The Deccan Traps eruptions overlap with the mass extinction event that killed the dinosaurs, and while the asteroid impact at Chicxulub gets most of the attention, some scientists believe the Deccan volcanism contributed to the extinction, either by itself or in combination with the asteroid impact. The volcanic gases could have caused acid rain, ocean acidification, and climate disruption. It's possible that life on Earth was dealing with volcanic stress when the asteroid delivered the final blow. We'll probably never know for certain how much the Deccan Traps contributed to the extinction versus the impact, but what's clear is that these massive volcanic eruptions reshaped India's geography and likely played a role in one of life's great crises. During explosive volcanic eruptions, blobs of molten rock get thrown into the air and cool while flying, forming what volcanologists call volcanic bombs. These are different from ash or small fragments. Volcanic bombs can be basketball-sized or larger, and they often take on aerodynamic shapes as they spin through the air. Some are shaped like ribbons or spindles twisted as they flew. Some are rounded with smooth surfaces. Some land still partially molten, deforming when they hit the ground, creating what's called a cowpie bomb because of its splattered appearance. What's remarkable is that these objects can land miles from the volcanic vent, ejected with such force that they sail through the air like artillery. Sometimes they're still glowing red from internal heat when they land. In the immediate aftermath of explosive eruptions, the landscape around the volcano is scattered with these bombs, random chunks of volcanic rock that fell from the sky, each one a frozen moment of the eruption's violence. Collecting and studying volcanic bombs helps scientists understand eruption dynamics, how forceful the explosion was, what the magma composition was, how far material travelled. But they're also just inherently fascinating objects, rocks shaped by flight, sculptures created by chaos. In Cameroon, there's a lake called Lake Nyos that sits in a volcanic crater, and in 1986 it released a cloud of carbon dioxide that rolled down the surrounding valleys and suffocated about 1,700 people and thousands of animals. What happened was this. CO2 from volcanic vents beneath the lake had been dissolving into the deep water over many years, accumulating to dangerous concentrations. Then something, possibly a landslide or just natural turnover in the lake's stratification, triggered a sudden release. The dissolved CO2 came out of solution all at once, like opening a shaken soda bottle, and formed a dense cloud that flowed downhill because CO2 is heavier than air. It was invisible and odorless, and people simply fell asleep and didn't wake up, overwhelmed by a gas that displaced the oxygen they needed to breathe. The tragedy led to an engineering solution. Degassing tubes were installed in Lake Nyos and similar lakes, allowing the CO2 to be released slowly and safely, instead of accumulating to catastrophic levels. You can see the tubes now, fountains of CO2-rich water spraying into the air, venting the gas that would otherwise build up below. It's a reminder that volcanic hazards aren't always dramatic, not always lava and ash, but can be subtle, invisible dangers that require understanding and intervention to prevent future disasters. The volcanic soils of Italy's Campania region, near Mount Vesuvius, have been cultivated for thousands of years, and they produce some of the world's most renowned wines, tomatoes, and crops. The same volcano that destroyed Pompeii also, over time, created the conditions for extraordinary agricultural abundance. The volcanic minerals, potassium, phosphorus, trace elements, break down over decades and centuries into soil of exceptional fertility. The wines made from grapes grown in these soils have distinctive mineral characteristics, what winemakers call terroir, a taste of the place itself, which in this case includes a taste of ancient eruptions. It's strange to think about, drinking wine and tasting volcanic rock, but that's what you're doing in a sense. The minerals that make eruptions devastating, the elements that were once part of molten magma, become the nutrients that feed vines and crops, that create flavors that sustain human life. It's a transformation from destruction to nourishment, from chaos to cultivation. And it happens everywhere that volcanoes and agriculture meet, in Java, in the Andes, in Hawaii. This conversion of volcanic material into the foundation of human food systems. The cycle continues: eruption, destruction, weathering, growth, harvest. Volcanoes take and volcanoes give, and humans have learned to wait for the giving part. The term pyroclastic flow comes from Greek words meaning broken fire, which is almost poetic for something so deadly. A pyroclastic flow is a fast-moving current of hot gas, ash, and volcanic rock that rushes down the slopes of a volcano during explosive eruptions, reaching temperatures of 1,000 degrees Fahrenheit or more, and speeds up to 450 miles per hour. Nothing can outrun a pyroclastic flow. They incinerate everything in their path, knock down forests, bury entire landscapes under deposits of hot ash and rock. They're one of the most dangerous volcanic hazards because they move faster than anyone can run, faster than most vehicles can drive, and they can change direction unpredictably, following valleys and topography. The only real protection is distance, being far enough away that the flow loses energy before it reaches you. When Pompeii was destroyed, it was a pyroclastic surge, a dilute form of pyroclastic flow that killed most of the people, not the falling ash. The heat was intense enough to kill instantly, but not always intense enough to burn bodies completely, which is why casts of the victims could be made. Pyroclastic flows are essentially avalanches of fire, gravity pulling superheated gas and rock downward with unstoppable momentum. They're beautiful in photographs taken from safe distances, terrifying up close, and absolutely lethal if you're in their path. If you want to find truly abundant volcanism, you'd need to leave Earth and travel to Venus. Our neighbouring planet has more volcanoes than any other world in our solar system, with over 1,600 major volcanic features identified on its surface. Some of these are enormous, shield volcanoes larger than anything on Earth, except perhaps Hawaii's Mauna Loa. The entire surface of Venus appears to have been resurfaced by volcanic activity relatively recently in geological terms, perhaps 300 to 500 million years ago, though recently in planetary geology still means before complex life existed on Earth. The question that fascinates planetary scientists is whether any of Venus's volcanoes are still active today. The planet's thick atmosphere makes direct observation difficult, but there's some evidence, changes in sulfur dioxide levels in the atmosphere, possible thermal hotspots detected by spacecraft, that suggests volcanism might still be ongoing. Imagine that. A planet wrapped in clouds of sulfuric acid, with surface temperatures hot enough to melt lead, and volcanoes that might still be erupting beneath that hostile sky. Venus is what happens when volcanism, atmosphere and greenhouse heating spiral into an extreme state. It's a cautionary example perhaps of how planets can become, showing us what Earth might have been like if conditions had been slightly different in our early history. The colour of volcanic rock tells you a story about its chemistry, about what was happening deep underground when the magma formed. Dark rocks, basalts and similar types, are rich in iron and magnesium, formed from mantle material that melted at great depths. They're heavy, dense, and they indicate the kind of volcanism you see at mid-ocean ridges or in Hawaii, where mantle material is reaching the surface relatively directly. Light-coloured rocks, rhyolites, dacites, contain more silica and often form from magma that's been sitting in crustal chambers, interacting with continental rocks, becoming more evolved and complex in composition. These lighter magmas tend to produce more explosive eruptions because their high silica content makes them viscous, trapping gases until pressure builds to violent levels. So you can look at a volcanic landscape and read its history in the colours of its rocks. Black basalt fields speak of deep source magma rising quickly. Light-coloured ash and pumice suggest magma that lingered in crustal chambers, changed its composition, built pressure, and finally exploded. It's like the volcano leaves a colour-coded record of its inner workings scattered across the landscape, waiting for anyone who knows the language to read it. When a volcano erupts and then goes quiet, sometimes the crater left behind fills with water over the following centuries, creating a crater lake. These lakes can be extraordinarily beautiful, often deep blue, surrounded by the remnants of the volcanic cone, pristine because they typically have no inflowing streams to bring sediment. Crater Lake in Oregon is the deepest lake in the United States, formed when Mount Masama erupted catastrophically about 7,700 years ago, and then collapsed, leaving a caldera that gradually filled with rain and snowmelt. The water is remarkably clear. You can see down nearly 100 feet in some places, because there are no rivers feeding into it, no sediment washing in. It's fed entirely by precipitation, which makes it exceptionally pure. The same pattern occurs in volcanic regions around the world. Violent eruption, collapse, silence, and then slowly, quietly, water fills the crater until what was once a vent spewing fire becomes a peaceful lake. There's something almost redemptive about this transformation, the way water heals the volcanic scar, The way the crater that once channeled destruction becomes a basin that holds life. Fish are introduced, ecosystems develop, people come to admire the beauty, and the lake's volcanic origin becomes just part of its story rather than its entire identity. On the Greek island of Santorini, archaeologists have excavated an ancient Minoan city called Akrotiri, buried by volcanic ash, around 1600 BC, when the island's volcano erupted catastrophically. Like Pompeii, the city was preserved by volcanic material, freezing a moment in Bronze Age Mediterranean life. But unlike Pompeii, no human remains have been found at Akrotiri. Not one. The buildings are intact, the pottery is still on shelves, the frescoes are still vibrant on the walls, but there are no bodies, no people caught in the disaster. This suggests that the inhabitants received enough warning, perhaps earthquakes, perhaps steam explosions, perhaps volcanic tremors, to evacuate before the main eruption. They left their city but saved themselves. We don't know where they went, whether they survived the wider catastrophe, or whether they eventually returned to find their home buried under meters of ash. But the empty city is a testament to the possibility of successful evacuation, a reminder that volcanic warning signs, if heeded, can save lives. The contrast with Pompeii is striking. Two cities, two eruptions, two very different outcomes for the people who lived there. Perhaps because one population had more warning time, or perhaps because they were more attuned to reading the signs their volcano was giving them. In the months and years following large volcanic eruptions, people around the world sometimes notice that sunsets are unusually vivid. Deep reds, brilliant oranges, colours more intense than normal. This happens because volcanic aerosols in the stratosphere scatter light in particular ways, filtering out certain wavelengths while allowing others to pass through. The result is sunsets of almost impossible beauty, skies painted in colours that seem too saturated to be real. After Krakatoa's massive 1883 eruption, artists painted these spectacular sunsets, and for years people wondered if the painters were exaggerating, if their depictions of blood-red skies were artistic license rather than observation. But they weren't exaggerating. The volcanic aerosols really did create sunsets of that intensity. There's something bittersweet about this, isn't there? A catastrophic eruption that killed thousands of people also created, as an unintended side effect, some of the most beautiful sunsets anyone had ever seen. Now, the same particles that cooled the global climate and disrupted weather patterns also made the sky glow with extraordinary colour at dusk. Nature doesn't do neat categories of good and bad. It does what it does, and humans experience both beauty and terror, sometimes from the same event, sometimes in the same moment. One of Jupiter's moons, a world called Io, is the most volcanically active body in the entire solar system. It's slightly larger than Earth's moon, but where our moon is cold and dead, Io is alive with volcanism. Hundreds of active volcanoes erupting constantly, some shooting plumes of sulfur and sulfur dioxide 300 miles into space. The surface is constantly being renewed, making it one of the youngest surfaces we know of in the solar system, geologically speaking. Nothing stays on Io's surface for long. It gets buried under new volcanic deposits within a few centuries. What drives this incredible volcanic activity? Tidal heating. Jupiter's immense gravity, along with the gravitational pulls from other large moons, stretches and squeezes Io as it orbits, generating friction and heat in the moon's interior, enough to keep it volcanically active despite its small size. It's a reminder that volcanism isn't unique to Earth, that the forces that create volcanoes, heat, pressure, geological activity, can operate on other worlds in different ways. If you could somehow stand on Io's surface in a protective suit, you'd see a landscape of sulfur in shades of yellow, orange and red, with volcanic plumes rising around you like geysers and Jupiter hanging huge in the sky above. It would be beautiful and utterly alien. When scientists sample volcanic gases, the steam and fumes emerging from vents and fumaroles, they're reading the volcano's chemistry, getting information about what's happening deep underground. The ratios of different gases tell you about the magma's composition, its temperature, how deep it originated. High concentrations of sulfur dioxide might indicate fresh magma rising from depth. Changes in the ratio of carbon dioxide to sulfur dioxide can signal that magma is getting shallower, that an eruption might be approaching. Each volcano has a unique chemical signature, like a fingerprint made of sulfur, carbon, and steam. By monitoring these gases continuously, volcanologists can detect changes that might precede eruptions, sometimes days or weeks in advance. It's not perfect. Volcanoes are complex systems and don't always follow predictable patterns, but gas monitoring has become one of the most important tools for forecasting volcanic activity. There's something almost intimate about this kind of monitoring, about sampling a volcano's breath to understand its intentions. It's a dialogue, in a sense, between humans and mountains, where the mountain speaks in chemistry, and scientists translate that language into warnings and understanding. The volcano doesn't speak clearly, doesn't announce its plans, but it does whisper in gazes, and we've learned to listen. In volcanic regions where groundwater seeps down to hot rock or magma chambers, pressure builds until superheated water erupts periodically as geysers. Like Yellowstone's Old Faithful is the most famous example, erupting roughly every 90 minutes with remarkable regularity, shooting steam and hot water 100 to 180 feet into the air. What's extraordinary about geysers is their clockwork behaviour. Old Faithful has been keeping time for thousands of years, a natural metronome driven by subsurface plumbing and thermodynamics. The cycle is simple in concept. Water seeps into an underground chamber. Heat from below raises the temperature until it starts to boil. Steam bubbles form and rise, eventually triggering an eruption that empties the chamber, and then the whole cycle begins again. But the precision is surprising. You can predict Old Faithful's next eruption based on the length of its previous one with reasonable accuracy. This regularity has made it a tourist attraction for over a century. People gathering on benches to watch, checking their watches, waiting for the moment when steam begins to billow and water shoots skyward. There's something deeply satisfying about this predictability in nature, about a process driven by heat and water and pressure that nonetheless keeps time like a clock, erupting on schedule, faithful to its patterns year after year, century after century. The Hawaiian Islands sit on the Pacific Plate, a massive section of oceanic crust that's slowly moving northwest at about 2 to 4 inches per year. This means the islands are being carried away from the volcanic hotspot that created them. As they drift away, the volcanoes become extinct, no longer fed by magma from below, and they begin to erode. The oldest Hawaiian islands, now in the northwest part of the chain, are heavily weathered and much smaller than they once were. Eventually they'll erode completely below sea level, becoming seamounts, underwater mountains that were once islands. Meanwhile, new volcanoes form over the hotspot to the southeast. Right now, the big island of Hawaii is volcanically active, but in a few million years, it too will drift away and go extinct, and the center of volcanic activity will shift to the next island in the chain, already forming underwater as a seamount called Loihi. This conveyor belt of island creation and extinction has been running for tens of millions of years, creating a chain of underwater mountains and islands stretching across the Pacific. It's a beautiful demonstration of how plate tectonics and volcanic hotspots interact. Yeah, how the same processes that build islands also ensure their eventual abandonment and erosion. Nothing is permanent, not even islands, not even mountains. They rise, they erode, they sink back beneath the waves. Sometimes if you're near an active volcano you can hear it. Not just the explosive roar of eruption, though that certainly happens during violent events. But there's also a subtler sound, a low, rumbling vibration, sometimes described as a hum or a deep rumble that comes from volcanic tremor deep underground. It's the sound of magma moving, of rock fracturing, of gases escaping, all transmitted through the earth to the surface where sensitive ears can detect it. Ancient peoples almost certainly heard this and interpreted it as the breathing or anger of gods dwelling underground. In Hawaiian tradition, these sounds were associated with Pele, the volcano goddess. In Roman mythology, they were the hammer of Vulcan. What's remarkable is how these interpretations, while mythological, captured something true. The volcano was alive in a sense, making sounds that indicated activity, warning of potential eruptions. Today, we have instruments that can detect and analyze these sounds, seismometers and infrasound sensors that translate vibrations into data. But the basic human experience remains the same. Standing on volcanic ground and feeling or hearing the mountain rumble beneath you. A reminder that the earth under your feet is not as solid and stable as it usually seems, that there are forces moving in the depths, forces that occasionally make themselves heard. There's a mineral called zeolite that forms in a peculiar way. When volcanic ash falls into alkaline water, perhaps in a lake or shallow sea, chemical reactions slowly transform that ash into this new mineral. Zeolites have an unusual crystalline structure, full of tiny channels and cavities at the molecular level, which makes them incredibly useful for modern industry. They're used in water purification systems because those microscopic channels can trap certain molecules while letting others pass through. They're used in detergents, in petroleum refining, in air separation, all because of their unique structure. It's strange to think about. Volcanic ash, the same material that buries cities and chokes the air, given time and the right chemical environment, transforms into something that helps purify water and clean industrial processes. It's another example of how volcanic destruction contains the seeds of later utility, how the materials created in violent eruptions can, over time, become resources. The transformation takes thousands or millions of years, chemical reactions proceeding slowly in the stillness after the chaos. But eventually what was ash becomes zeolite. What was destruction becomes a tool for removing impurities, filtering, refining. Even at the molecular level, volcanoes create structures we've learned to use. Sometimes, underwater volcanic eruptions create temporary islands, new land that rises above sea level for a few months or years before wave action erodes it away again. These ephemeral islands challenge our definition of what constitutes land. If an island exists for 6 months and then disappears, was it really an island? Does it count? Geologically, it certainly happened. Rock and ash accumulated above sea level. Birds might have landed on it, waves crashed against its shores. But then the unconsolidated material, not yet hardened into solid rock, gets worn away by currents and storms, and the island subsides back beneath the waves. It's like watching creation and destruction compressed into a time frame we can observe, the geological processes that usually take millennia happening in months. Sometimes these temporary islands complicate international maritime law. If an island appears in disputed waters, does it create territorial claims? What happens when it disappears? These questions aren't purely academic. They've come up multiple times when submarine volcanoes have created short-lived islands. But beyond the legal complications, there's something almost poetic about these transient lands, these places that exist only briefly, reminding us that the boundary between ocean and land, between existence and non-existence, can be surprisingly fluid. On May 8th, 1902, Mount Pelée on the Caribbean island of Martinique erupted with almost no warning, sending a pyroclastic surge down its slopes toward the town of Saint-Pierre. The cloud of superheated gas and ash reached the town in minutes, travelling at tremendous speed, and killed approximately 30,000 people almost instantly. In the entire town there were only 2 confirmed survivors. One was a prisoner named Louis-Auguste Siparis, held in an underground cell, essentially a stone box with only a small grating for ventilation. His confinement, meant as punishment, became his salvation. The thick stone walls protected him from the heat and gases that killed everyone else. When rescuers found him days later, he was badly burned through the grating, but alive. The other survivor was a shoemaker who lived on the edge of town in a house with thick walls. The contrast is stark. 30,000 dead, 2 alive. It's a reminder of how quickly volcanic disasters can unfold, how little time there was for evacuation, how arbitrary survival can be. Siparis later joined the Barnum and Bailey Circus, travelling as the only survivor of St. Pierre, showing audiences his scars and telling his story. He lived another 30 years, a walking testament to both the horror of that morning and the strange chance of his survival. When we look at Mars through telescopes and send rovers across its surface, we find volcanic rocks everywhere, massive lava flows, volcanic plains, enormous shield volcanoes. These rocks tell us that Mars was once volcanically active on a scale that dwarfs anything on Earth. But here's the mystery. We don't know if any of Mars's volcanoes are still active. There's some indirect evidence, methane in the atmosphere that might come from volcanic vents, possible recent lava flows that seem only a few million years old, but we haven't directly observed an eruption. Mars lacks the tectonic activity that drives most volcanism on Earth, so if volcanoes there are still active, they're operating on very long cycles, perhaps erupting once every few million years. Or perhaps they've all gone extinct and Mars is now geologically dead, its volcanic age ended. These ancient lava flows suggest that Mars was once a world of fire, a planet where massive eruptions reshape the surface repeatedly. What would it have been like to witness Olympus Mons in its active phase, erupting into Mars's thin atmosphere? We'll probably never know. But the rocks remain, evidence of a volcanic past that may or may not have a future. About 74,000 years ago, a supervolcano called Toba, located in what's now Indonesia, erupted in one of the largest volcanic events in human history. The eruption was so massive that it may have triggered a volcanic winter lasting years, with global temperatures dropping significantly. Some scientists believe this eruption reduced the human population to just a few thousand individuals, a genetic bottleneck that nearly extinguished our species entirely. Yeah, the evidence comes from genetic studies showing that all humans alive today descended from a relatively small population that existed around that time. If this hypothesis is correct, then every person alive, every human who has lived since, is descended from the small group of survivors who made it through the aftermath of Toba's eruption. We're all here because our ancestors endured that volcanic winter, found ways to survive when food was scarce and the sun was dimmed by stratospheric ash. It's a humbling thought, isn't it? That our species came that close to extinction, that a volcanic eruption nearly ended the human story before it really began. Of course, the hypothesis is debated. Not all scientists agree on the severity of the bottleneck or whether Toba was the primary cause, but the possibility alone is sobering. Some volcanoes are fed by multiple magma chambers at different depths, each with its own distinct chemical composition and characteristics. This means the same volcano can erupt in very different ways at different times, depending on which chamber is active and whether the magmas mix or remain separate. Imagine a mountain sitting above multiple reservoirs of molten rock, each one brewing its own particular chemistry. Sometimes an eruption draws from just one chamber, producing lava with a specific composition. Other times magmas from different chambers mix on their way to the surface, creating hybrid compositions, and occasionally a volcano will switch chambers entirely, changing its personality between eruptions. This makes prediction difficult. A volcano that erupted gently last time might explode violently next time if a different, more gas-rich magma chamber becomes active. Volcanologists try to understand these plumbing systems using seismic imaging, chemical analysis of erupted materials, and monitoring of ground deformation, but it's challenging work. The systems are complex, three-dimensional, and largely hidden. So each volcano becomes a puzzle, a network of underground chambers and conduits that we can only partially see, and that complexity means surprises are always possible. When volcanoes erupt, the gases they release, particularly sulfur dioxide, can combine with water in the atmosphere to create acid rain, precipitation that's significantly more acidic than normal rain. This acid rain can fall hundreds of miles from the eruption site, damaging forests, acidifying lakes and streams, affecting ecosystems that were never threatened by the eruption itself. Fish populations decline, trees lose their leaves, crops suffer. It's a far-reaching impact that extends the volcano's influence well beyond its immediate vicinity. But here's the interesting part. Over longer timescales, these same chemicals that create acid rain eventually settle out and weather into the soil, where they become nutrients. The sulfur becomes sulfate, which plants need. The volcanic gases that killed trees in the short term contribute to soil fertility in the long term. It's another example of volcanic impacts operating on different timescales. Destruction in the immediate aftermath, enrichment over decades and centuries. Nature doesn't experience this as contradictory. It's all part of the same cycle. Elements move from deep in the earth to the atmosphere, fall to the ground, get taken up by living things, eventually get buried and subducted and start the cycle again. The acid rain is just one moment in that endless circulation. In the Afar region of Ethiopia, there's a volcano called Erta Ale that has contained a lava lake for over a century, one of the longest lasting lava lakes known. Unlike most volcanoes that erupt periodically, Erta Ale just sits there with molten lava exposed at the surface, glowing day and night, occasionally sloshing and overflowing, but never fully crusting over. Visitors who trek to the summit, it's a difficult journey across one of the hottest, most desolate places on Earth, describe it as looking directly into the planet's molten heart. The lava lake provides a window into processes that usually happen deep underground, hidden from view. Scientists study Erta because that constant exposure of active lava is rare and valuable. They can see how lava circulates in the lake, how gases escape, how the crust forms and breaks. There's something hypnotic about watching a lava lake. The surface is always moving, convecting, with cooler crust forming and then breaking apart as hotter material rises from below. The glow pulses. Sometimes fountains of lava burst upward. It's dynamic, alive in a way that solid rock never is. A reminder that beneath the stable surface we walk on, there's heat and motion. A liquid interior that occasionally reveals itself. Lahars are volcanic mud flows, fast-moving mixtures of water and volcanic debris that can remain dangerous for years after an eruption ends. They form when volcanic material mixes with water, maybe from rain, maybe from rivers, maybe from melting glaciers on the volcano's peak. The result is something like wet concrete flowing at high speed down river valleys, picking up more material as it goes, capable of travelling dozens of miles from the volcano. Lahars can destroy bridges, bury towns, and change river courses. What makes them particularly insidious is their timing. They can occur long after the eruption itself, triggered by heavy rains falling on loose volcanic deposits. So even when the eruption is over and the mountain is quiet, the danger persists. Communities downstream from volcanoes have to remain vigilant during rainy seasons, watching for signs of lahars, sometimes for years. The 1985 eruption of Nevado del Ruiz in Colombia generated lahars that travelled 60 miles and killed more than 23,000 people in the town of Armero. Most of those people died hours after the eruption, not from lava or ash, but from this mixture of mud and debris flowing down river valleys in the darkness. It's a reminder that volcanic hazards extend in space and time beyond the eruption itself. When geologists study volcanic deposits, the layers of ash, the hardened lava flows, the scattered pumice, they're reading the history of a landscape's most dramatic moments. What now looks like a peaceful valley might have been carved by a massive pyroclastic flow 10,000 years ago. That gentle hill might be a remnant of an ancient volcanic cone, worn down by millennia of erosion. The colourful bands in cliff faces often represent different eruptions, each layer a separate event separated by centuries or millennia of quiet. This kind of geological detective work has revealed that many landscapes we think of as peaceful were shaped by catastrophic events. The Pacific Northwest's Columbia River Gorge was partially carved by massive floods from glacial lakes, but also shaped by volcanic eruptions and lava flows. New Zealand's stunning lakes occupy volcanic calderas. Much of Iceland's dramatic geography comes from ongoing volcanic activity and glacial floods called jökullaups. The more we study, the more we realise that catastrophe is part of the normal geological process, that the landscapes we love were often forged in violence and then softened by time. It changes how you see the land, knowing its history, understanding that the quiet beauty you're witnessing is sometimes the healed scar of ancient destruction. And some volcanic minerals have a property called phosphorescence. They glow in the dark after being exposed to light, storing energy and releasing it slowly as a soft luminescence. It's not the dramatic glow of molten lava, but something gentler, more mysterious. These rocks seem to hold sunlight inside them and release it gradually when darkness falls. The effect comes from impurities in the crystal structure, trace elements that trap electrons when exposed to light and then release them slowly, producing that characteristic glow. Ancient peoples who found these glowing rocks must have thought they were magical, stones that captured the sun's essence and kept it burning through the night. Even today, knowing the physics behind it, there's something enchanting about a rock that glows. It's a reminder that volcanoes don't just create the obvious products, lava, ash, explosions, but also these subtle, unexpected properties in the minerals they form. The same geological processes that build mountains also create crystals with strange behaviours, rocks that seem to defy the boundary between living and non-living, storing and releasing energy in ways that make them feel almost animate. Venus is wrapped in clouds of sulfuric acid, and those clouds likely come from volcanic outgassing. Volcanoes releasing sulfur compounds that react with the atmosphere to form the acid droplets that now envelop the entire planet. This volcanic contribution to the atmosphere has helped create Venus's runaway greenhouse effect, where temperatures at the surface reach about 900 degrees Fahrenheit, hot enough to melt lead. It's a cautionary tale, in a way, of what can happen when volcanic gases accumulate in an atmosphere without being recycled effectively. On Earth, carbon dioxide from volcanoes is absorbed by weathering rocks and by the ocean, maintaining a rough balance. But Venus apparently lost that balance, perhaps because it lost its water early in its history, and without water to weather rocks and absorb gases, the volcanic CO2 and sulfur just accumulated. The greenhouse effect intensified, temperatures rose, any remaining water evaporated, and the planet entered a state it's been locked in for hundreds of millions of years. So Venus shows us that volcanism alone doesn't determine a planet's fate. It's volcanism plus atmosphere plus oceans plus a dozen other factors interacting in complex ways. And small differences in the initial conditions can lead to radically different outcomes. Certain volcanic rocks contain tiny bubbles, vesicles, where gas was trapped as the lava cooled. These bubbles are like time capsules, preserving samples of Earth's atmosphere from when the lava solidified. By carefully extracting the gas from these bubbles and analysing it, scientists can study what the atmosphere was like millions of years ago. The ratios of nitrogen to argon, the amounts of carbon dioxide, even trace gases, all preserved inside volcanic rock. It's extraordinary when you think about it. These rocks let us breathe, chemically speaking, the same air that existed when dinosaurs walked the Earth, or even earlier. We can compare ancient atmospheres to today's and track how the composition has changed over time. And some volcanic rocks are billions of years old, from when Earth's atmosphere was very different, lower in oxygen, higher in other gases, and the bubbles in those ancient lavas carry that information forward through time. Volcanoes are not just agents of change, but also archivists, inadvertently recording atmospheric conditions in the rocks they create, preserving information that lets us understand our planet's past. We often use the phrase tip of the iceberg to mean that most of something is hidden, and it applies just as well to volcanoes. What we see above the surface, the mountain, the crater, the lava flows, represents only a small fraction of the total volcanic structure. Below ground, there's an entire plumbing system of magma chambers, conduits, dikes, and sills extending deep into the earth. For every mountain we see, There's a vast, mostly invisible network of channels where magma has intruded into the surrounding rock. Some of these structures extend miles underground. The magma chambers can be enormous. The one beneath Yellowstone is measured in thousands of cubic kilometers. We can map these underground structures using seismic imaging, essentially using earthquakes as X-rays to see inside the Earth. But our resolution is limited and much remains uncertain. So when we look at a volcano, we're seeing the exit point of a system that extends far deeper than we can observe directly. It's like seeing a tree but not its roots, or seeing a building but not its foundation. The mountain is just where the system intersects the surface. The real structure, the part that controls how and when eruptions happen, is mostly hidden. Volcanic islands are isolated from continents by hundreds or thousands of miles of ocean, often become biodiversity hotspots, places where evolution takes unique paths, creating species found nowhere else on Earth. The Galapagos Islands, formed by volcanic activity, are the most famous example. Darwin's observations there of finches and tortoises with variations from island to island helped him develop his theory of evolution by natural selection. Volcanic islands provide natural experiments in evolution, new land with no existing life, gradually colonized by whatever seeds, spores, insects and birds manage to arrive across the ocean. Those colonizers then adapt to local conditions, often evolving into new species. Hawaii has hundreds of species found nowhere else. Madagascar, separated from Africa by volcanic activity in the ancient past, evolved an entirely unique ecosystem. Iceland, one of Earth's youngest major islands, is still in the early stages of this process. So volcanoes don't just create land, they create opportunities for life to diversify, for evolution to experiment. The isolation provided by volcanic islands in the middle of oceans has generated an outsized proportion of Earth's biodiversity. Destruction and creation, extinction and speciation. They're often intertwined in volcanic landscapes. During some volcanic eruptions, observers have reported seeing strange electrical phenomena called lightning sprites, brief flashes of light that occur high above the volcanic cloud, reaching up into the mesosphere, the layer of atmosphere where meteors burn up. These sprites are different from the volcanic lightning that occurs within the ash cloud itself. They're taller, more fleeting, harder to photograph, and they connect the volcano to parts of the atmosphere normally untouched by weather or geological processes. Sprites were long thought to be optical illusions or myths, but high-speed cameras have confirmed they're real, brief discharges of electricity that extend upward from storm systems, including volcanic eruption clouds, into the upper atmosphere. They last only milliseconds, but they're enormous, sometimes extending 30 miles vertically. What causes them is still being studied, but they seem to be related to the strong electrical fields created in the eruption column. It's one of those phenomena that reminds us how much we still don't fully understand about volcanic eruptions, how many subtle and complex processes are happening simultaneously. A volcanic eruption affects not just the ground and the lower atmosphere, but reaches up to touch the edge of space. In places like Iceland, New Zealand and the Philippines, volcanic heat provides geothermal energy that powers entire cities, heats homes, and generates electricity for millions of people. The principle is simple. Where magma sits close to the surface, it heats groundwater, and that hot water can be tapped to drive turbines or used directly for heating. Iceland generates nearly all of its electricity and heat from geothermal sources, a remarkable achievement made possible by its location atop the mid-Atlantic ridge. What was once pure danger has been converted into sustainable energy. The same heat that can destroy cities during eruptions provides cheap, clean power during quiet periods. Yeah, it's one of the most direct examples of humanity learning to live with volcanoes productively, to take advantage of geological forces that can't be stopped or controlled, but can be harnessed. Geothermal energy is renewable on human timescales. As long as the volcanic system remains active, the heat keeps flowing. It's a partnership between humans and the restless earth, a way of turning geological hazard into resource, making the volcano work for the people who live on its slopes. Sometimes, instead of erupting from a central vent at the top of a mountain, lava emerges from a long crack in the ground called a fissure, creating what's called a fissure eruption. These can produce spectacular curtains of fire, continuous walls of lava fountaining along a crack that might extend for miles. The 2014 to 2015 Holuhraun eruption in Iceland was a fissure eruption that created a river of lava covering about 33 square miles, flowing across the landscape like a slow-motion flood of molten rock. Fissure eruptions are common in Iceland because the island sits on a diverging plate boundary where the crust is being pulled apart, creating long cracks that magma can exploit. These eruptions can last for months, steadily pouring out lava, adding new land to the island. They're generally less explosive than eruptions from steep-sided volcanoes because the magma can escape relatively easily through the fissure rather than building pressure underground. But they can be enormously productive in terms of lava volume, reshaping large areas over relatively short periods. Standing near an active fissure eruption, one watching lava fountain along a crack in the earth that extends beyond what you can see is one of geology's most surreal experiences. In Tanzania, there's a volcanic lake called Lake Natron, with such unusual chemistry that it calcifies animals that die in it, preserving them in a kind of natural mummification. The water is extremely alkaline, pH levels sometimes above 10.5, due to volcanic minerals, particularly sodium carbonate, that leach into the lake from surrounding volcanic deposits. The water is also very salty and can reach temperatures of up to 140 degrees Fahrenheit in some areas. Most life can't survive in these conditions, but there are exceptions. Flamingos breed there in huge numbers because the hostile environment protects their nests from predators, and certain algae and bacteria thrive in the alkaline water, giving parts of the lake a red or pink colour. But when birds or other animals die and fall into the lake, the alkaline water can preserve and even calcify their bodies, coating them with mineral deposits. Photographer Nick Brandt documented these calcified creatures, creating haunting images of birds and bats preserved in lifelike poses on the lake shores. The lake is beautiful in a stark way, hostile to most life but essential to some, its unusual chemistry a direct result of the volcanic landscape that created it. Around the world, volcanologists use a standardized alert system to communicate volcanic threat levels to the public and to authorities. The system uses color codes: green for normal, baseline activity, yellow for advisory, when there's elevated unrest but no immediate threat, orange for watch, when an eruption is possible in the near term, and red for warning when an eruption is imminent or already underway. This universal language helps communities prepare regardless of which volcano is active or which country they're in. The system exists because volcanic crises often unfold over days or weeks and clear communication is essential. People need to know whether to go about their normal lives, to prepare for possible evacuation, or to evacuate immediately. The color codes provide that clarity, cutting through the complexity of volcanic monitoring data to give actionable information. Of course, implementing these warnings requires infrastructure, monitoring networks, communication systems, evacuation plans, and not all volcanic regions have adequate resources. But the framework exists, near a recognition that volcanoes don't respect political boundaries and that standardized communication saves lives. When scientists drill ice cores from Greenland or Antarctica, cylindrical samples of ice extracted from deep within glaciers, they find layers of volcanic ash scattered throughout the ice, each layer marking a past eruption somewhere in the world. These ash layers are incredibly useful for dating the ice and understanding Earth's volcanic history. Because volcanic ash from major eruptions can spread globally in the stratosphere before settling, the same eruption might leave a signature in ice cores from both poles, allowing scientists to correlate dates between cores and create precise timelines. Each ash layer tells a story, where the volcano was located based on the ash's chemical composition, how explosive the eruption was based on how widely the ash spread, and when it happened based on the ice layer it's found in. Some of these ash layers are from eruptions that occurred thousands of years before any written records existed, eruptions that no human remembered but that the ice preserved perfectly. The archives in Greenland's frozen depths contain a history of fire, a record of every major eruption that sent ash into the stratosphere, waiting to be read by anyone who drills deep enough and looks carefully enough. In the deepest parts of the ocean, along mid-ocean ridges and in other volcanically active areas, there are hydrothermal vents, places where seawater seeps down through cracks in the ocean floor, gets heated by magma below, and then erupts back into the ocean as superheated mineral-rich water. Some of these vents are called black smokers because the dissolved minerals precipitate when the hot water meets the cold ocean, creating dark plumes that look like smoke. Around these vents, entire ecosystems exist based on chemosynthesis rather than photosynthesis. Communities of life that derive energy from the chemicals in the volcanic water rather than from sunlight. Giant tube worms, eyeless shrimp, unusual clams and bacteria that can withstand extreme temperatures all thrive around these vents. It's life powered by volcanoes, by heat from Earth's interior, functioning in complete darkness under crushing pressure. These ecosystems demonstrate that life doesn't absolutely require sunlight, that the energy for living systems can come from geological sources. The discovery of hydrothermal vent communities revolutionized biology's understanding of what life needs and where it might exist. Perhaps in similar vents beneath the ice of Europa or Enceladus, anywhere in the universe where water meets volcanic heat. There's a green gemstone called peridot, the birthstone for August, that forms in the deep mantle and is brought to the surface in volcanic rocks, particularly in a type of rock called basalt. Sometimes volcanic eruptions bring up enough peridot that it scatters across the landscape, and in a few places, like certain beaches in Hawaii, you can find tiny peridot crystals mixed in with the sand. They're small, usually just a few millimeters, but they catch the light with the distinctive olive-green color. Most people walk right past them, not recognizing these tiny gems for what they are. Now, the same mineral in larger crystals is cut and sold as jewelry. But here on a volcanic beach, they're just part of the sand, free for anyone who notices them, little fragments of the deep earth brought up by volcanic forces, and deposited where waves can sort them. It's a reminder that gems aren't rare in the geological sense. They're just concentrated in certain places and overlooked in others. The volcano doesn't distinguish between peridot and ordinary olivine. It brings up whatever was down there, and whether we call it a gemstone or a mineral depends on size and quality, not on any inherent difference in origin. A caldera is a large depression that forms when a volcano's magma chamber empties, either through eruption or through underground drainage, and the overlying rock collapses into the void. Some calderas are so large that people live inside them without necessarily realizing they're in a volcano's crater. The Campi Flegrei caldera near Naples, Italy, is partially occupied by the city itself, home to more than 3 million people if you include the greater metropolitan area. The caldera is about 8 miles wide, formed by a massive eruption 39,000 years ago, and it's still considered active, with ongoing ground deformation and minor earthquakes. Living inside a caldera means living directly above the volcanic system, surrounded by the remnants of past catastrophic eruptions. The ground occasionally rises and falls as magma moves below, a phenomenon called bradyseism, lifting and lowering the land by feet over the course of years. For the people who live there, this is normal, part of the landscape's character. It's another example of humans choosing to stay in volcanic areas despite the risks, making that calculation that the benefits, the culture, the economy, the sense of home, outweigh the dangers, and perhaps they're right in their own context. After all, the last major eruption was 39,000 years ago. In human terms, that's almost forever. Our moon, which now seems so cold and dead, was likely volcanically active billions of years ago. The dark patches we see when we look up at the full moon, the areas that people have called the man in the moon or various other patterns, are ancient lava flows, massive eruptions that filled impact basins with basaltic lava around 3 to 4 billion years ago. These flows are called maria, Latin for seas, because early astronomers thought they might be bodies of water. They're not. Of course, they're hardened lava, cooled and solid for billions of years. The moon's volcanism apparently shut down long ago as its interior cooled and its heat budget depleted. There are no active volcanoes now, no magma chambers, no eruptions. The lava flows we see are frozen in time, unchanged for longer than complex life has existed on Earth. Standing on the moon and looking at these ancient lava plains would be like standing on a record of the early solar system, seeing volcanism from an era when the moon was still geologically active, still warm inside, still capable of erupting. Now it's quiet, and those dark maria are monuments to its volcanic past. Inside certain volcanic rocks, scientists have found grains of shocked quartz. Quartz crystals that have been deformed by immense pressure, their internal structure altered in distinctive ways. This kind of deformation usually indicates either a massive explosive volcanic eruption or a meteor impact, two of the few natural events that can generate the pressures needed to shock quartz. The presence of shocked quartz helps geologists distinguish between different types of catastrophic events. If you find shocked quartz in a layer of rock, along with volcanic ash, it suggests an eruption of extraordinary violence. If you find it in a layer with materials that don't match local geology, it might indicate an impact that excavated and shocked rock from deep below. The same type of deformation appears in rocks from known impact sites like Chicxulub in Mexico, the crater left by the asteroid that contributed to the dinosaurs' extinction. We're so shocked quartz links two forms of cosmic violence: asteroid impacts and massive volcanic eruptions, events that operate on different scales but can produce similar effects on individual mineral grains, leaving signatures that persist for millions of years. Modern volcanic monitoring is remarkably sophisticated, involving networks of seismometers that detect earthquakes and tremors, gas sensors that measure changing compositions of volcanic emissions, thermal cameras that detect temperature changes, GPS stations that measure ground deformation with millimeter precision, and satellites equipped with synthetic aperture radar that can detect swelling or subsidence from space. All of this data flows into monitoring centers where volcanologists watch volcanoes in real time, looking for patterns that might indicate increasing activity. They can watch a mountain breathe, see it inflate as magma accumulates underground and deflate as magma drains away from thousands of miles away. The GPS stations can detect movement of just a few millimeters, revealing how the volcano is deforming as pressure changes below. Gas sensors can detect subtle changes in the ratio of different compounds, hinting at what's happening in the magma chamber. It's an impressive technological achievement, this ability to monitor volcanoes remotely and continuously. Of course, the technology is most available in wealthy countries, and many of the world's most dangerous volcanoes are in regions with limited monitoring infrastructure. But where the technology exists, it saves lives by providing warnings that were impossible to give just a few decades ago. About 252 million years ago, in what's now Siberia, a volcanic event began that would last for perhaps 1 million years and cover an area larger than Europe with lava. This is called the Siberian Traps, and it's associated with the Permian-Triassic extinction, the most severe extinction event in Earth's history. An estimated 96% of marine species and 70% of terrestrial species went extinct. It's sometimes called the Great Dying, and while the exact mechanisms are debated, the volcanic eruptions almost certainly played a major role. The sheer volume of volcanic gases released, carbon dioxide, sulfur dioxide, possibly methane from coal beds ignited by the lava, would have dramatically altered the global climate and ocean chemistry. Temperatures likely spiked from greenhouse gases, oceans may have become acidic and oxygen depleted, and ecosystems collapsed worldwide. Life came closer to complete annihilation than at any other time in the past 500 million years. The fact that anything survived is remarkable. But survive it did, and in the aftermath, new forms of life emerged to fill the empty niches. The Siberian Traps remain as evidence of volcanism's power at planetary scales, a reminder that volcanic activity can be not just a local hazard, but a force capable of reshaping life on Earth. Some volcanic minerals exhibit fluorescence. They glow under ultraviolet light, revealing colours and patterns invisible in ordinary daylight. Shine a UV lamp on certain volcanic rocks, and they might light up in greens, oranges, or reds, colours that come from trace elements trapped in the crystal structure during formation. Uranium compounds fluoresce green, tungsten compounds glow blue. Rare earth elements produce various colours. It's like the rocks have a hidden layer of decoration that only reveals itself under the right conditions. Collectors of fluorescent minerals often seek out volcanic specimens because the rapid cooling and unique chemistry of volcanic environments can create striking fluorescent displays. But even beyond collecting, there's something wonderful about the idea that rocks have properties we can't perceive in ordinary light, that there are layers of reality we miss without the right tools to see them. The volcano creates these minerals, incorporates these trace elements, and the result is rock that glows under UV light, carrying colours that existed all along, but that we needed a different kind of light to reveal. After Mount Pinatubo's massive 1991 eruption in the Philippines, you have the sheer weight of volcanic deposits, ash, pumice, and other materials several feet thick over large areas, caused the ground to sink in some places. The land literally subsided under the burden of volcanic ejecta, creating subsidence bowls where the surface dropped several feet. Buildings that survived the eruption itself then had to deal with their foundations sinking unevenly. Roads buckled. Drainage patterns changed. It's a reminder that volcanic impacts aren't limited to the dramatic moments of eruption, heat, ash clouds, lava flows, but continue for years afterward as the landscape adjusts to the new weight and distribution of material. Lahars continued for years every rainy season as the loose volcanic deposits washed down river valleys. The weight of the deposits compressed and compacted underlying sediments. The local geography was permanently altered. Even decades later, the landscape around Pinatubo is still adjusting to what happened in 1991, still settling into a new equilibrium. The eruption was brief in geological terms, hours to days of active eruption, but its consequences played out over years and continue to play out now, more than 3 decades later. When we look at Mars with our most sophisticated instruments, analysing rocks from different regions and different ages, we find that volcanic activity there didn't happen all at once, but rather occurred in episodes spread across billions of years. Some Martian volcanic rocks are ancient, formed over 3 billion years ago when the planet was young. Others appear to be only a few million years old, recent in geological terms, though still far predating human existence. This suggests that Mars pulsed with volcanic life periodically, with long dormant periods in between, rather than burning steadily like Earth does. Perhaps Mars's interior cooled unevenly, with episodes of heating and melting interspersed with quiet periods. Perhaps mantle plumes rose intermittently from deep within the planet. We don't fully understand the pattern yet, but the rocks tell us that Mars's volcanic story wasn't a simple narrative of active youth followed by dead old age. It was more complex, with the planet returning to volcanism again and again across vast stretches of time. And there's always the possibility, unproven but intriguing, that somewhere on Mars, in some deep chamber we haven't detected yet, magma still waits, and the volcanic story isn't quite finished. The study of volcanic rocks has contributed to our understanding of so many things beyond volcanoes themselves. It helped us understand plate tectonics, the pattern of volcanic activity along mid-ocean ridges and subduction zones revealed how Earth's surface is divided into moving plates. It helped us understand planetary formation. By studying the composition of volcanic rocks, we learned about the differentiation of Earth's layers, how heavy elements like iron sank to form the core while lighter materials rose to form the crust. It even helps us understand Earth's core, that unreachable realm of liquid iron nearly 2,000 miles below our feet, because volcanic rocks sometimes contain minerals and isotopes that originated at the boundary between the core and mantle. Each lava flow is, in essence, a sample brought up from depths we can never drill to, a messenger from the interior. When we analyse these rocks carefully, they tell us about pressure and temperature conditions deep underground, about chemical compositions we can't otherwise access, about processes happening in realms we can only study indirectly. Volcanoes are geology's gift to surface-dwelling scientists, windows into the planet's interior, delivering samples and information from a world we can never visit. Over volcanic regions where large magma chambers exist underground, gravity is slightly weaker than normal. This happens because magma is less dense than solid rock, so a massive chamber of molten material creates a subtle deficit in gravitational pull compared to what you'd expect from solid rock. Satellites equipped with sensitive instruments can measure these tiny variations in Earth's gravitational field from space, creating maps that reveal subsurface structures. These gravity anomalies help scientists locate and estimate the size of hidden magma chambers, understanding volcanic plumbing systems without drilling. It's remarkable, really. Gravity itself becomes a tool for seeing underground. The satellites orbit hundreds of miles up, measuring variations in gravity so subtle that you'd never feel them standing on the ground, and from those measurements scientists can infer the presence of molten rock miles below the surface. It's one of those examples where physics that seems abstract and theoretical, gravitational field variations measured to incredible precision, becomes immediately practical, telling us where magma lurks, where volcanoes might erupt, where the earth is hollow with heat rather than solid with stone. Not all volcanoes erupt with molten rock. In Indonesia, there's been a mud volcano called Lucy erupting continuously since 2006, not with magma, but with boiling mud, water, and gases. It started suddenly, and in the years since it has displaced about 60,000 people, burying entire villages under thick layers of grey mud. The eruption was likely triggered by drilling for natural gas nearby, though this remains controversial. Either the drilling destabilized underground pressures, or the timing was coincidental and the eruption would have happened anyway. Regardless of the cause, Lucy behaves in many ways like a conventional volcano. It has a central vent. It creates new mounds and deposits as material erupts and spreads. It releases gases. But instead of glowing lava, it produces mud. Thick, grey, boiling mud that flows outward, hardens, and creates a surreal landscape of grey mounds and craters. Mud volcanoes are actually fairly common worldwide, though most are much smaller than Lucy. They form where subsurface pressure forces mud and water upward, often in regions with oil or gas deposits. They're a reminder that the term volcano encompasses more than just magma eruptions, that Earth has multiple ways of releasing pressure from below, some fiery, some muddy, but all driven by similar forces. As volcanic rocks cool, the magnetic minerals within them align with Earth's magnetic field at that moment, essentially recording the direction of the planet's magnetic poles. Once the rock is solid, that magnetic signature is locked in place, preserved for millions of years. By studying these paleomagnetic records in volcanic rocks of different ages from different locations, scientists discovered something extraordinary. Earth's magnetic poles wander over time, and occasionally they flip completely, with north becoming south and south becoming north. This discovery of magnetic field reversals was crucial evidence for plate tectonics. It explained the striped patterns of magnetic anomalies on the ocean floor, where new rock forms at mid-ocean ridges and records the field direction at formation. Each eruption creates a time capsule of Earth's magnetic field, a snapshot frozen in stone. By collecting these snapshots from around the world and from different time periods, geologists have reconstructed the history of our planet's magnetic field, going back millions of years. And it's all because volcanic rocks remember the magnetic field they cooled in, preserving information that would otherwise be lost. One of the persistent mysteries in volcanology is this: what exactly triggers a volcano to erupt after centuries or millennia of dormancy? We can monitor the symptoms, the earthquakes as magma rises, the ground deformation as chambers fill, the changing gas compositions, but we don't fully understand the deep mechanisms that decide when a sleeping volcano wakes. Is it simply a matter of magma accumulating until pressure exceeds the strength of the overlying rock? That's part of it, certainly, but eruptions don't always follow that simple pattern. Sometimes volcanoes that seem ready to erupt don't, and sometimes volcanoes that showed minimal warning signs suddenly explode. There are clearly processes we don't yet understand, threshold points and feedback mechanisms happening deep underground where we can't observe directly. Each volcano seems to have its own personality, its own quirks in how it behaves. Some give weeks or months of clear warning, others erupt with minimal precursors. We've learned to read many of the warning signs, but volcanoes still surprise us with their timing and intensity. There's humility in admitting this, that despite all our technology and understanding, we still can't perfectly predict volcanic behavior. We can be prepared, we can monitor carefully, but the final trigger, the moment when dormancy becomes eruption, remains partly mysterious. In Earth's early history, when the sun was about 30% dimmer than it is today, the planet should have been frozen. Simple physics suggests surface temperatures would have been below the freezing point of water, and yet we have geological evidence that liquid water existed, that oceans were present, that the early Earth was not a frozen snowball. This is called the faint young sun paradox, and one of the proposed solutions involves volcanic outgassing. Early Earth was likely more volcanically active than today, and the greenhouse gases released by those ancient eruptions, primarily carbon dioxide, may have kept the planet warm enough for liquid water despite the dimmer sun. Without volcanic gases warming the atmosphere, Earth's water would have frozen, and life might never have begun. So volcanic activity may have been crucial for maintaining habitable conditions on the young Earth, yet creating a greenhouse effect strong enough to compensate for the sun's relative weakness. It's another way that volcanoes appear in Earth's story as creators rather than just destroyers. They helped establish the conditions that allowed life to emerge, pumping gases into the atmosphere that kept the oceans liquid and the planet habitable. Here's something we know with certainty: volcanic eruptions will continue. Earth's interior is still hot, still convecting, still generating magma. Tectonic plates will keep moving, subduction zones will keep producing volcanoes, hotspots will keep feeding volcanic islands. We can't predict exactly when or where future eruptions will occur, but we can be certain they will happen. That's not pessimism, it's just geology. The same processes that have been operating for billions of years will continue operating for billions more, until eventually, far in the future, Earth's interior cools completely and volcanic activity ceases. But that won't happen for a very long time, likely billions of years from now. In the meantime, we live on an active planet, a world where the interior is alive with heat and motion, where mountains sometimes explode and new land sometimes forms from molten rock. This is normal for Earth, part of its character, part of what makes it a dynamic, changing world rather than a dead, static one. And so we study volcanoes, we monitor them, we learn to live with them, because they're not going away. They're part of the package of living on a geologically active planet. Long after humans are gone, whether that's thousands, millions, us or hundreds of millions of years from now, volcanoes will still be reshaping Earth's surface, Tectonic plates will still collide and separate, magma will still rise, eruptions will still occur. Volcanoes are indifferent witnesses to deep time, operating on schedules that dwarf human history. The volcanoes we study today are just the current generation in a lineage that stretches back to Earth's formation and will continue until the planet's interior finally grows cold. Islands will rise from the ocean and erode away. Continents will drift into new configurations. Mountain ranges will grow and wear down, and through all of it, volcanic activity will be one of the primary mechanisms of change, one of the processes that keeps Earth's surface dynamic rather than static. There's something both humbling and oddly comforting about this perspective. Our moment, human civilization, all of recorded history, is just a brief pause in an enormously long story. The volcanoes were here long before us, reshaping the world according to forces that originate deep underground, and they'll continue that work long after we're gone, indifferent to our absence just as they were to our arrival. The word volcano ultimately reminds us that humans have always tried to explain these mountains of fire, to make sense of their power and unpredictability. Ancient Romans named them after Vulcan, seeing a god's forge in the smoke and rumble. Hawaiians saw the goddess Pele, whose temperament matched the volcano's moods, creative and destructive, nurturing and wrathful. Other cultures had their own explanations, their own mythologies built around these mountains that breathed fire. Then came the scientific understanding, plate tectonics, magma chemistry, seismology, new explanations based on observation and measurement rather than divine agency. But in a way, all these explanations capture something true. Volcanoes are divine in their power, in their ability to create and destroy on scales that dwarf human capacity. They're scientific in their mechanisms, following physical laws we can study and partially predict. And they're poetic in their beauty, in the way lava glows against dark rock, in the way new land emerges from the sea, in the contradictions they embody: fire and ice, destruction and creation, danger and fertility. The word volcano carries all of this, the ancient attempt to understand, the modern knowledge we've gained, and the wonder that persists even after we understand the mechanisms. Some things are worth naming carefully, worth thinking about from multiple angles, worth approaching with both science and poetry. And so, we've travelled through 100 facts about volcanoes, from the origin of their name to the deep mysteries that remain unsolved, from the smallest details of glowing minerals to the planetary scale impacts of massive eruptions. We've seen how volcanoes have shaped our world, creating atmospheres and oceans, building islands and mountains, destroying cities and preserving them, ending species and creating conditions for new ones to emerge. Perhaps what's most remarkable about volcanoes is this fundamental duality they embody. They are both destroyers and creators, both deadly and life-giving. The same eruption that buries a town creates soil that will feed generations. The same gases that poison the air helped create the atmosphere we breathe. The same forces that terrify us also build the landscapes we find beautiful. We live on a restless planet, a world still warm inside, still changing, still very much alive in the geological sense. The volcanoes remind us of this. They're evidence that beneath the stable surface we walk on every day, there's heat and motion, molten rock and tremendous forces, all of it hidden until the moment when the mountain decides to show us what it's made of. And maybe that's enough to think about as you drift towards sleep, that we live on a planet that's still being made, still reshaping itself, still writing its story in fire and stone. The volcanoes were here before us and will be here after us, patient in their way, destructive when necessary, creative when conditions allow, indifferent witnesses to the passage of time and the small brief lives of everything that walks across their slopes. Sleep well, and thank you for exploring these mountains of fire with me tonight. Until next time.